All right, the next section we have here, 3.1, is really where, not where the calculus begins. Calculus does begin with limits, but I think for most people, this is really where we start doing the things that you hear about in calculus. We take derivatives, and this is where we're going to talk about the definition of the derivative. So in a previous video a while back, actually, I believe 2.1, the first section we did, I talked about this Desmos calculator, and I showed you how you can move some sliders around, and I created an interactive graph, and that's available for you. With that interactive graph, a lot of the ideas that we're going to talk about in this section were really seeds that we had planted way back in that video and in that section. The idea of calculating an average rate of change and then taking the average on a smaller and smaller and smaller interval, honing in on or closing in on the point in question. And essentially, we determined way back when, the beginning of this chapter, or the beginning of chapter 2, I should say, now that this is chapter 3 starting, that the instantaneous rate of change really is approximated by average rates of change. And we can define the instantaneous rate of change as a limit of average rates of change where those intervals over which the averages are taken, they contain the point where we desire the instantaneous information. So I'm not going to read through all of this text. You can take a look at it. There's a lot of text in this section because I believe it's best to really just hash it out in the way that I feel makes sense to me. So I won't read this verbatim by any means, but I will talk about how I'll highlight the important parts here. So important thing here is that the tangent line is the line to a graph where it's always at a point. So this is the tangent line at this point right here. Why that point? Because it is at this point where the slope of the line perfectly matches the curvature of the curve. Some people say the tangent line is the line that crosses the graph only once, and that's not true because, for instance, what if we had a graph like this, here's some kind of sinusoidal curve here. The tangent line, right, or maybe let's make this a little bit less sinusoidal and a little bit more varied. All right, so here's some arbitrary graph I just drew. If I do the tangent line right here at this point, notice that it crosses way more than once. So this is still a tangent line. It's a tangent line to the curve at this point here. So don't think of it that it's not that the tangent line's not allowed to cross. It's really that it perfectly captures the shape of the graph at a particular point in question. So when you want to construct a tangent line, you have to construct that tangent line at that point. You have to know the point where you want to construct the tangent line because you need to know what the curvature is at that location. And that curvature value is what effectively you dictate the slope to be for that line. So we've got a tangent line here. And the slope of the tangent line, the slope of this line so the slope of the tangent line is the instantaneous rate of change. Of this function at that point. Okay? So down here we actually have the definition, slope of a tangent line. So if you remember the way we calculated this in the past, we would take some sort of axis system. We assumed we had some sort of function here. And then what we would do is, let's say we've got a point A, say x equals A, and then at this point x equals A, we are going to then move some distance away. Let's move a separation of h units away, and then we have another point. And now if we connect these two dots together, this forms the secant line. And the slope of the secant line is the average rate of change. So now what we do, and the mechanic here of this limit is a mechanism. We can kind of think of this as like a radio dial, and we're just going to turn down the volume. We're going to turn down that distance from whatever h is, right? Maybe it's 10 units away, but we can think of like sliding it down, or as a dial. We're going to just dial it down, and effectively what that's going to do is it's going to take this distance here, h, and it's going to make it smaller. It's going to just make it smaller, and effectively what that's going to do is that means this point at x equals a plus h, it's going to move that dot closer and closer and closer towards the point on the graph at x equals a. And what's going to happen here is we're going to get these varying secant lines, and the slopes of these secant lines are all going to change. And effectively, as that point gets closer and closer and closer, it's going to approach this slope here, which is the tangent line. So right here, the thing we're taking the limit of, this expression, this is just slope formula. This is y2 minus y1 all over x2, which is a plus h, minus x1, which is a. If you simplify that, you're just left with h. So this right here is just your regular old rise over run, but simplified. So then we take the limit of rise over run, and we get the slope of the tangent line at some value x equals a. Now there's another way that we can write this. It's this notation over here. It's still slope formula. It's x2 minus x1, or sorry, y2 I should say, y2 minus y1 over x2 minus x1. It is a different formulation, but it is equivalent to this formulation. These are the two, these pieces right here are called difference quotients, because it is a quotient of differences. Sometimes that term will come up, so you should be aware of what it is. All right. So here in this slide, I outline exactly what this process is. We start with a secant line, this red one, that is a distance h away, and then this blue one is just some intermediary one. I basically I made h a little bit smaller here, so you can see the sliding secant line pattern, and eventually it will approach the tangent line.